Hi everyone, I'm Thomas Lively. I'm a software engineer at Google working on WebAssembly tools. And today I would like to talk about module splitting, so decomposing WebAssembly modules with the goal of improving their load time. This is a very open question. We haven't actually done any work at all on this yet. It's kind of just an idea floating out there that we'd like to do sometime soonish. So I thought that this would be a good opportunity to share that very early stage idea and get more feedback about it. So without further ado, here's the problem we're trying to solve. No one wants to wait for the WASM to load, right? That's not the useful part of WebAssembly, waiting for it to load, so we want to minimize that as much as possible. So when you load a WebAssembly module, on the web at least, you have to download it first. And WebAssembly is designed in a way so that as you download it, it can be compiled in a streaming fashion. So we can kind of compile while we download, and after it's compiled and instantiated, then we can start running it. So if we want to decrease the time we wait before we can run the module, then we need to reduce that download and compile time. And the way you do that is by making the module smaller. Right? The smaller the module, the quicker it'll compile, and the sooner we can run it. But we can't really wave a magic wand and just make all the modules tiny. So what we really need to do is split off the code. And here's the main idea. If we can take our module and split it into two, so that only the code we need at startup is initially downloaded and compiled, then we could start running the code just after that initial bit is loaded, and in parallel, download and compile the rest of the code so that it's ready when we need it. So this is not just theoretical, right? We know that if we can reduce the size of code, it will improve startup performance. And we know this because there are folks out there already doing something similar. So I want to share this example from Adobe, and they published a blog post about this. So they have a technique that they call WASM swapping for their Acrobat.js product. So what they do is they make two builds of Acrobat.js, one with exceptions disabled and one with exceptions enabled. To be fully correct and handle all the things it's supposed to handle, this code base does depend on having exceptions enabled. But for common cases, it'll run correctly without them. And when they disable exceptions, they get a much smaller binary because Emscripten has to do a bunch of crazy code transformations to support exceptions today. So what they do is they just download and compile their build without exceptions enabled, and then they run it. And because it's smaller, they get to run it sooner. And if everything goes well and it's not a crazy edge case PDF, then that's it. They just run normally forever. However, if that code base without exceptions enabled runs into a situation where it needs exceptions, then what the application does is download and compile the second build, the bigger build with exceptions enabled, and it just reruns the workflow with that new binary. So this works because the work of displaying a PDF is idempotent, right? They can just throw away what they've done, download a new build, and just run it again from the start, and that's okay. But most applications are not like that. You can't just throw away all the work you've done so far and rerun it from the start. Second, Emscripten supports disabling exceptions and compiling, and it supports enabling exceptions and compiling. So they don't need to do any craziness in the C++ tool chain to make this work. They just need to do 2 different builds and then sort of juggle them on the client in JavaScript. So this is pretty clever and pretty cool. And the results are that when they introduced this technique, the initial package size went down almost by half, right? So on the left there, that yellow bar is the exceptions disabled package size. And you can see that the first page load time over there on the right also went down by about half. So it looks like that the load time for the page is about proportional to the size of the binary. So this is pretty strong evidence that anything we can do to make the initial download smaller will be effective in improving our page load time. But what we really want is something that's more general, right? We want this to work for basically all applications, not just idempotent applications that work okay without exceptions, but sometimes need exceptions, right? That's very niche. So we need a more general solution. So that's the problem. And for the rest of the talk, I'm going to briefly cover WebAssembly module structure. Not assuming that everyone is an expert on WebAssembly yet, and the mechanics of how you decompose a module into 2 modules. All right. So given that you know how you want to decompose it, what mechanically do you do to make that happen? Then we want to put this in the real Emscripten toolchain. So I'll give an overview of Emscripten to sort of contextualize this and show how this functionality can fit into the existing tool chain. And then I'll talk a little bit about the policy of determining what to defer. All right, we know how to defer things, but figuring out what code to put in that second deferred module is mostly an open question. And then I'll finish with some observations and additional open questions, and then hopefully we have time to discuss. So getting started here, first of all, we have functions in a WebAssembly module, and they can be imported or exported. So here I've designated imported modules, functions with this I, and exported functions with this E. So a WebAssembly module only interfaces with the outside world via things it imports and exports. Second, we have a memory. All right, WebAssembly is a Harvard architecture, so functions do not live in memory. But especially for compiling things like C and C++, we need a memory that we can read and write bytes from. So we have that. And the memory itself is also an object that can be imported or exported. We have a table. So the table basically stores function references, which are opaque. So function references cannot be stored in memory because they don't have a defined bit pattern. And this is an important security feature of WebAssembly. So to make up for that, we have this table. And so a function pointer in C compiles down to an index into this table, and the index can be stored in memory. And then in order to call a function indirectly, we load that index from memory and then run an instruction that looks up that index in the table and then calls the corresponding function. And finally here we have globals. So WebAssembly globals are kind of like registers that persist between function calls. So they're not used for C globals, for example, which need to be in memory. So we actually only use a few globals at the moment. Mostly, the most important one is stack pointer. So we have a stack in linear memory in addition to the sort of WebAssembly stack machine stack. And all of the address taken variables in C or C++ or Rust or any of those languages would go in that in-memory shadow stack, we call it. And so we have this stack pointer that is exactly like a normal native stack pointer register. And then we also have a few globals for managing TLS, thread level storage. But that's really it. There aren't many globals. So WebAssembly modules, you need to compile them. So you download some bytes from the internet or load them from a file, and then you run webassembly.compile on it, and that gives you a module. A module is stateless and clonable, so you can send a module, copy it, and send it to a worker thread, or a web worker. And so if those two modules share the same memory, then that's how we implement threading in the web. Modules, because they're stateless, they don't have imports and they don't have exports, so you can't actually run a module. To do that, you need to instantiate it. And the process of instantiation requires supplying the imports that the module needs. And then once instantiation is done, it exposes all the exports. So then you can run code in the module. For example, if a module exports main, then after it's instantiated, you can run main on that instance. And of course, it is stateful. It's running code, so the memory and the table actually have content in an instance. And you can access them if they're exported. So this thing where you don't get exports until after instantiation, but instantiation requires all of the imports to be available, that'll be important in a minute. So moving on, and holler if there are any questions. Let's talk about how we would decompose a WebAssembly module. So we'll start with the simple case. We have this sort of call graph in our module. We have a function called callee, and it's called by another function called caller. And what we're going to do is we're going to split caller out and put it in that deferred module that gets loaded after the initial code. So we split main.wasm into main.wasm and deferred.wasm. And we still want to be able to call this callee function from caller. So we need to make callee available to that deferred module. So we export it, import it into deferred.wasm, and now it's visible just like any other function, and caller can call it directly, just like before. So that's a pretty simple case. Just export the dependency, import it into the deferred module, and then everything works just like normal. So what if we want to defer the loading of the callee instead? So now we've flipped the arrow. So caller is going to stay in the main WebAssembly module, and callee is going to get deferred. So we can try doing the same thing, now exporting the callee from the deferred module and importing it in the main module, and then doing a call just like normal. But this won't work. Remember that exports are only available after instantiation, and all of the imports need to be available before instantiation. So at the time we instantiate main.wasm, callee hasn't been downloaded yet. It's in the deferred module. It's not available, so we can't import it directly. So this setup has a causality violation and unfortunately won't work. But there's no problem that can't be solved in computer science with an extra layer of indirection. So that's exactly what we can do here. Instead of importing callee directly, because it hasn't been downloaded and compiled yet, we can import a JS trampoline function. And so if we call this trampoline function before deferred.wasm has been downloaded and compiled, it'll throw an error or something we'll worry about later, right? So it'll have some default behavior when callee is not yet available. And then once the sort of JS runtime has downloaded and compiled and instantiated deferred.wasm, then we can go patch that trampoline function in JS to then redirect calls to callee. So if we do an indirection through JS, we can sort of fix this problem of imports needing to be available before exports. But having to round trip through JS every time we want to call callee is a little unfortunate, because that's going to be kind of expensive. You know, there's some cost for crossing the WASM to JS boundary. And it's not really portable to WASM runtimes that don't have JS. So it'd be cool if we could come up with a pure WASM solution to this. And this is a lot closer. So instead of using a JS function for the indirection now, we're using a table, a WebAssembly table. So that table is declared in main.wasm and exported. And when deferred.wasm is downloaded and compiled and instantiated, it'll import that table. So main and deferred are both sharing this table. So they can both change its contents and make indirect calls to function references in that table. So when deferred.wasm is downloaded, it'll run table.set to store a reference to callee in the table. And then in main.wasm, when caller is run, it'll do a call indirect instruction pointing to that index in the table and indirectly call callee. So there's still a little cost here, right? We're now doing an indirect call instead of a direct call, but at least we don't need to go through JavaScript. So this should be a little simpler and faster and more portable. So that's basically it for functions. Globals are going to be pretty similar, although we have so few of them. Really what you want to do is just put them all in main and export them and then import them in deferred, right? So we don't really need to do this complex logic about deferring individual globals, especially not for C++. Other tool chains might use more WebAssembly globals, so they might want to be able to defer those globals into the second module, but we won't worry about that here. So again, holler if there are any questions so far. But now we'll look at Emscripten, how Emscripten works, so that we can figure out how this module splitting should fit into the toolchain. So at its core, Emscripten is really just Clang and WASM-LD. So these are both upstream LVM projects. Obviously, Clang is the C and C++ compiler we all know and love. And WASM-LD is the WASM-specific version of LLD, which is LLVM's linker. So just like a native toolchain, you put your source files into Clang, it spits out object files. In WebAssembly, object files have the structure of a normal WebAssembly module, but they also have relocations in a special custom linking section. So we do have a sort of custom object file format for WebAssembly, and that's documented in our tool conventions repo. So you can look up that format if you want and use it in any tool chain. And WASM-LD takes static library archives and object files and resolves all the relocations and spits out a WASM module, just like in a native compilation and linking setup. But the story doesn't end there. So obviously we need system libraries. If you can just use bare Clang and WASM-LD if you don't depend on libc or libpthread or anything else, right? If it's all self-contained code, then that's fine. But most applications will need a libc. And that libc requires system calls. So WebAssembly, as a sort of core specification, does not have any specified system calls. Remember, everything that you need to do to interact with the outside world needs to be imported into the module. And there are no specified imports. Separately, there's a different spec going on in the WebAssembly community group called WASI, which is a standard set of syscalls for WebAssembly, but it's focused on server-side applications, and so it's not really available on the web. So in Emscripten, the syscall implementations are all in this JS file. So moving along, WASM LD emits this a.wasm sort of linked module, and we have this JS file that Emscripten generates. But they both need to be optimized. So for WebAssembly, we have a tool called WASM opt, which I'll talk a little bit more about in a bit. And it's just a WASM to WASM optimizer, and it can shrink modules produced by LLVM by, if I remember correctly, it's about 20%. And the reason for that is WebAssembly is highly structured, unlike most LLVM targets. So there are a lot of WebAssembly specific optimizations that WASM ops can do that LLVM just doesn't do right now. And because WASM ops can use a special WASM specific IR, it's much easier to write new optimizations in WASM ops than it would be to write them in our LLVM backend. And we also optimize the JS. But beyond optimizing them separately, we can also optimize them together. So there's another binarian tool called WASM Meta DCE. And what it does is dead code elimination across the WebAssembly and the JavaScript. So it can look at the call graph across that WASM JS boundary to figure out what code it can cut out. So that's kind of cool. This Emscripten really tightly integrates the JS and the WebAssembly, and sort of where the dividing line is more or less an implementation detail of Emscripten. So zooming out, the big picture is this. At the compilation stage, EMCC is really just a thin wrapper script around Clang. It's not really doing anything extra. Emscripten provides both C and JS libraries. So it emulates a sort of POSIX system on the web for easily portable code. And it's really the link stage that's really doing all of the interesting work, including optimizing the WASM and JS separately and together. So looking at this picture, it's clear that if we split a WASM module, we're going to need some extra JS to know how to load the deferred module, right? And link it in and get everything working. So we're going to need to make JS changes. And of course, we're going to need to make WASM changes just to split the module in the first place. So that's most similar to this WASM Meta DCE step here. So if we were to sort of copy the structure of how that's done, then what we would want is a new binarian tool, maybe called WASM split, that takes a WebAssembly module and splits it, emits the two new WebAssembly modules, and then emits enough information about what should happen in the JS that Emscripten can then take care of emitting all the JS to handle loading the new module and hooking it up. So all of this should be totally transparent to the user. So binarian seems like the correct place to do this kind of transformation. Binarian sort of generally is a compiler and toolchain infrastructure library for WebAssembly. It has a whole bunch of tools, WASM opt as we saw, WASM Meta DCE as we saw, also a few others including WASM to JS, which compiles WebAssembly to JavaScript as the name implies. And Emscripten uses that one to support older browsers that don't even have WebAssembly implementations. And binarian is used in a whole bunch of tool chains. Rust uses it for sort of last-minute optimizations. Emscripten uses it for a whole bunch of things, as we've seen. And AssemblyScript and another language called Grain and even Haskell use it. They sort of link with it and use it as a compiler backend for doing all of their optimizations going to WebAssembly. So we know the mechanics of how to split up code and defer it. We know sort of how we're going to fit that into the tool chain. And so now we have the policy question of what do we defer, right? Which functions do we split out and put in that second module? Which functions do we keep in the first module? So there are a few methods that we could use to try to figure this out. First of all, we can just ask the user. So we found in Emscripten that a lot of users want really fine control over the code that gets emitted. So a lot of users are happy to provide lists of functions that should or should not be instrumented. So in this case, we could have options for users to tell us, you know, always defer these functions or never defer these functions. So that's a pretty good starting point. And after that, we can do some static analysis to sort of propagate that information, figure out what other functions should be deferred or not. So in the call graph, any function that dominates a function that will not be deferred also shouldn't be deferred, right? You never want to have to defer something that sort of in the timeline, in the trace of the execution, sort of will happen after something that hasn't been deferred. And sort of the converse is true. So anything that is dominated in the call graph by a deferred function should probably also be deferred because it's not going to be useful to have in that initial module. But user input, not all users are going to want to put in all the effort to figure out which functions should be deferred themselves, nor should they have to. That's a lot of work. So it would be good to have some profile guided sort of heuristics for figuring this out. And so, of course, with all profile guided optimization, you can either do it with sampling or with instrumentation. And one of the cool things in the WebAssembly space is that Chrome Developer Tools actually already supports taking performance profiles. And so this picture here is it's a screenshot of the developer tools taken from their documentation. And it's showing that you can actually save the profile, the performance profile, which is a huge blob of JavaScript with timestamps and function information and all this stuff. So it would be pretty cool if we had Binarian ingest these Chrome DevTools performance profiles and use that to guide the optimization. I think that'd be, you know, a nice tying together of the whole ecosystem here. And then, of course, since we're working in Binarian anyway, it's always an option to instrument the binary. So we could insert, you know, a counter for each function and detect what timestamp each function is first called at. So we can, you know, really precisely categorize functions as either being run early or run late or never run at all. And we can use that information to guide the decision of what functions to defer. So even if we had a total ordering of the first timestamp at which a function is going to be run across all possible executions of a project, we'd still have this question of where's the threshold, right? How much should we defer and how much should we keep in that initial module? So I don't really have anything concrete to say here because this is really going to be a matter of tuning, right? We're going to have to set a threshold and maybe we deferred too much and now we're waiting in the middle of this application for the new code to load. Or we deferred too little and you know, it always runs fine, but we're still waiting too long for that initial module to load. And I expect this to be different from application to application too. So we probably want to give the user some control over the thresholds here. And of course, there's a difference between late code and dead or exceptional code. We saw in the Adobe case that they're absolutely fine simply not loading that exception code if they don't need it, right? So they don't need to load it eagerly. They can really load it lazily. For late code that you know is going to be run, just not at the beginning, you don't really want to lazily load it, because then you end up waiting, in the middle of your application for this new code to be loaded, compiled, and hooked up so it can be run. So for late code that gets deferred but will definitely be run at some point, you really want to eagerly load that. So maybe we should give users options to, eagerly load some deferred code and lazily load some other deferred code. And there's a whole design space of how that could work as well. So hard to say until we actually implement this and experiment with it, but definitely something we need to be thinking about as we go forward with this. So I've mentioned a few times that you don't want to be stuck waiting for your deferred code to load. But we should talk about what actually happens when you do need to wait, since networks are unpredictable, and this is definitely going to happen at some point, and it needs to be gracefully handled by the application. So in this example, the application is compiled, it's instantiated, and so the embedder.js on the website kicks it off by calling main, which in turn calls foo, which in turn calls bar. But bar is in this deferred module, and it hasn't been loaded yet. It's still working on downloading that in the background. So what are we going to do in the meantime? We can't just spin waiting for bar to be loaded, because that will lock up the entire browser, and you won't be able to scroll, and you won't be able to click on things, and it'll just be a terrible user experience. So we really need to get back out of this WASM and go back to the browser event loop so that the application can keep running while we wait for bar to be loaded. So what we really want here is some sort of resumable exception or delimited continuation or stack switching mechanism, so that we can sort of preserve the stack we have so far, but still exit the application, go back to the JavaScript. And then later, once the deferred code has been loaded, we want to resume right back where we were and keep going, calling bar and continuing to run the application. Unfortunately, WebAssembly does not support delimited continuations or stack switching or resumable exceptions today, although there are proposals in flight for all of those things. So in the grand scheme of time, eventually we'll be able to use those mechanisms. But for now, we need to use a thing called asyncify. Asyncify is a code transformation implemented in Binarian that allows basically exactly what we need. So when we get down to bar, we can kick off asyncify and tell it to unwind the stack. So what this does is it just returns out of every function and along the way stores all of the local state into memory. So it stores all the WASM locals into memory, and it also stores counters saying which part of each function it's currently in. So it stores into memory all of the information you need to later restore the stack. So once the deferred code is loaded, we can call the asyncify API again from JS and tell it, okay, restore the stack now. And what that does is walk down the control flow in each function, skipping directly to the parts that we need to skip to restore the stack, using these big if-else blocks that the asyncify code transformation inserts, and restoring all of the locals from memory, and really just putting things back the way they were. So once the deferred code is ready, we restore the stack, and from there, we can continue running just like normal. Asyncify is quite a big hammer. It's very important, right? This is an important problem to be able to solve, so it's a good thing we have Asyncify. The overhead from using Asyncify is about 50% for both code size and for run speed in the worst case. So it'll probably be a little better in this case, because once that deferred code is ready, you never need to unwind or restore the stack again, right? So all those branches will be correctly predicted. But it's a little unfortunate that we have to do this for now. So we eagerly await the stack switching and delimited continuations proposals. So that's pretty much everything I've got. So a common question when this topic comes up of automatic code splitting is, why not just use dynamic shared libraries?
Thomas,
yep.
Can I interrupt you for a sec?
Yes.
So I forgot to do something at the beginning, and your actual last slide just segues naturally into it, which is I forgot to announce the next seminar. So the next seminar is actually going to be by Donald Pinckney on his work with WASM-K with his advisor Arjun Guha, where they independently designed an extension to WebAssembly for delimited continuations. And have implemented it in WASM time and been able to do a bunch of experiments on showing like performance relative to Asyncify and stuff. So that'll be Friday, October 24th at 4 Eastern time. So actually, I didn't actually realize there's going to be a connection with this, but it turns out there is. So that's great. But yeah, so that's the announcements. Which I didn't want to interrupt discussion, so I figured I should do that now. So back to you.
All right. Thanks. Yeah, I look forward to that. That sounds really interesting. So why not use shared libraries? Emscripten does support DL open, so you can just chip down a normal dynamic object and DL open it and call it from there. But dynamic shared libraries really solve a different problem, right? They're about source code organization and how you sort of manage your dependencies dynamically. They're not about splitting things between code that's run early and code that's run late, right? You could do that, but you'd have to re-architect your entire application around that idea. And that's not something that you do in a native application, because this whole early-late splitting is really only useful on the web where you have these download times. And Emscripten's all about portability. So we don't want people to have to re-architect their entire applications. So that's why shared libraries aren't a great solution to this problem. A note about function outlining. Right now, we don't do any function outlining, but it's an optimization that we would like to implement. And it complements this module splitting idea really nicely. Because especially if we did the instrumentation, so we could tell exactly which basic blocks were run early or late. And we could outline basic blocks that are only run late in the execution and put those basic blocks as separate functions in the deferred module and make the initial module even smaller. This is kind of similar to hot-cold splitting, except it's early-late splitting. And LLVM has a bunch of infrastructure for doing profile-guided hot-cold splitting. So even though we want to do this ultimately in binarian, it's possible we could reuse some of that LLVM infrastructure or do it in both places, which would just be twice as useful. And then there's a bunch of open questions we have that we'll have to implement it and see how it turns out. So the threshold where you choose to decompose the module, will it depend on the network quality, right? So if they have a poor quality network and it takes longer to download things, does a different threshold make sense? What about the compilation throughput, right? What if the client has a bad network but a really fast computer, so compilation super quick, or maybe the other way around? And will the difference be significant between different network qualities and different compilation throughputs. If it is, I fully expect some users to do multiple builds of their project with different tuning parameters for the threshold for splitting, and then to try to detect the conditions on the client to choose which build to use for that particular client. People really care about getting every single ounce of performance out of these things.
You have a question, Thomas.
Okay, great.
Paulo, can you use your mic, or do you want me to read it for you?
Let's see.
Yes, I was muted. Sorry. Hello. So yes, I have a question. I think that some engines, at least V8, I think, compile all the functions in the module when it is instantiated. And does this contribute to the problem? Could we also minimize the load time if we lazy compile the functions when they are called the first time?
Yeah, so I'm pretty sure V8 in particular does compile the functions eagerly at compile time. But I think you're right, there might be some engines that do it lazily at instantiation time. And
actually,
this also
V8 has V8 has multiple strategies. So now there's two compilers, Liftoff and Turbofan. Liftoff is a streaming compiler that compiles as the bytes are loaded, and then Turbofan comes in afterwards, asynchronously.
But if I'm not wrong, both compilers, if a function is compiled twice with Turbofan and with Liftoff, in any case, even if it's never invoked.
No, Turbofan's only invoked for hot functions, I believe.
Oh wait, no, with WebAssembly too. Well, yes, of course. Yes. Okay, yes.
Yeah. So yeah, engines do all sorts of tiering strategies. Like Francis said, it's common to have a sort of baseline compiler that does that streaming compilation up front. And then for hot functions in particular, at runtime, asynchronously recompiling and reoptimizing them and then patching them in. But that's not doing it at instantiation time, right? That's at runtime. So it helps this tiering. Having low tiers helps page load time because the streaming compilation can get the application running faster. And then the second tiers, the optimizing compilers, can increase throughput later for those hot functions, but don't have much of a bearing on load time. So this toolchain level technique should be complementary to that engine level technique, because even with the streaming compiler, if you need to streaming compile less code up front, it's still going to go faster. And we saw that in the Adobe case in particular.
And the idea is you could use the tooling to determine which functions are at the head of the module, and then you could have actually start running the program as you're compiling it, even on the engine side, so they can complement each other there. If you were to do something like the lazy system that Paulo is describing.
Yeah, that information could also be fed to the engine. It could be very useful in this sense. Yes.
Can you take an interrupt?
Mm-hmm.
Heejin had a question too, if I can let her go first.
All right, yeah, so Heejin asked, would splitting modules to more than 2 pieces help? In general, it might help solve some problems. It wouldn't help with the specific problem of reducing the initial load time for the page, right? So the initial load time, the time when you can start running your module, is only bound by the size of that initial code that you download. But if your application has a sort of special structure where it goes in multiple phases, and each phase runs drastically different code, then yeah, I could totally see that splitting it up sort of by phase and then lazily, perhaps, downloading the code for each phase would totally make sense.
So I have some experience in this area. We built in a previous existence, I built a service, a CDN service that did the very similar kind of thing for JavaScript. It was automatic. So I think one of the problems with getting programmers to identify which functions can be deferred or not is that they get it wrong. And especially if you have a global application, you know, what needs to be deferred in China is different to what needs to be deferred in APAC or in America or EU. So, and also managing all those different builds is extremely difficult. So we did it as a service. What we did was we instrumented a small proportion of actual clients, and we figured out, and we measured which functions were run when, and used that information to decide the split. And we actually had an arbitrary number of modules that we could split our code into. It turned out that I mean, there's some special things about JavaScript, and there are some special things about the situation then, which are different to the WebAssembly case. We could not afford the asynchify route because it would be JavaScript and asynchify is just way too difficult to get right.
Yeah.
So what we actually did a blocking read when we're doing the deferred load. We did a blocking one. I actually built two services, so there's two versions of this. The net of this was that with the automatic service and JavaScript being whatever the hell it is, we could expect the expected code size reduction of their initial load was approximately 40%. That's including the overhead of the stubs that you have. All right, so this was basically, you know, the JavaScript overhead is different, and it'd probably be a little bit bigger than for WebAssembly. But so with all of that overhead, the expected code size reduction, I would imagine, is going to be similar. All right, so with an automatic system that measures which functions can be deferred, by the way, that's non-trivial, but anyway, by measuring the functions that can be deferred, you would get a pretty substantial code size reduction.
Yeah, I don't think we wouldn't want to ship the instrumented builds to users, right? You'd sort of
we did actually. Actually we did. So that's one of the advantages of being a CDN.
Mm-hmm.
So what we did was we were able to take a raw JavaScript, or in this case it'd be a raw WebAssembly, without any special partitioning, all right? Nothing special partitioning, all right? And then measure. We would instrument like a small proportion of actual users.
Yeah.
Continuously, in fact. So, you know, there was always like 1% of users or 0.1% of users that got instrument, because it changes. So like it's different at 9 o'clock in the morning and 8 o'clock at night. It's different.
Mm-hmm.
And then what you do is you use the service uses that instrumentation to recalculate the optimization. This is how we did it.
One of the nice things about implementing this in Binarian is that it's such a general sort of framework that gets built into a lot of tools that you could build a service like that using Binarian, doing that exact same thing. Or you could do what we'll probably do in Emscripten, which is make it more of a, you know, exercise that's really only visible to the developers, right? Where the developers create an instrumented build, run some test cases or automated whatever on it.
They'll get it wrong. They'll simply get it wrong.
Well, then I hope someone builds
Anyway,
it.
that was the determination that we had anyway. So maybe you're wrong. Maybe I'm wrong. All right. And I think one thing that we didn't have, which I think would be is potentially really interesting, is the sort of async await or asyncify kind of transformation. That would, because one of the big issues for us was safety, and JavaScript makes that really, really hard.
Yeah.
So actually, there's a question I have. So with the module linking proposal, one of the issues that strikes me about this is that you're forced to export a bunch of things that you might not necessarily want to export.
Yeah.
And maybe the module linking proposal is a way of kind of like wrapping that up again.
Yeah, that's possible. I'd have to go look at the details of the module linking proposal to, say for sure. But in general, in Scripting specifically, we don't care so much about exporting extra things, because Scripting is not really trying to use WebAssembly for its isolation guarantees, right? It's more of an implementation detail of, let's just compile this big trusted C++ application to the web. So I don't think that'll be a problem for Scripting specifically, but for the more general problem for other tool chains, I think that will be a valuable addition. Yeah.
Forgive me if I disagree.
So
I mean, I think it's not your business really. If I'm developing an application, you don't get to say what I want to export or not.
I think what Thomas is describing is the JS shell around the WebAssembly modules will still make sure things are bottled up. But I was wondering, Thomas, if there's what kind of changes do we need to make to WebAssembly to support this, and what kind of changes would be helpful? Like the ones that come to mind is, I forget, can we import export mutable globals yet?
Yes, that was a just passed MVP proposal. I'm not sure Safari implements it yet, but that was standardized a long time ago, at least.
Okay, so because you'll need that for the stack, obviously, the shadow stack.
Yeah.
And then what was the other thought? So right now you have actually it's on the slide. You have to import this thing that you're going to call, that's sort of it's a stub, right? Is there something we can add to either WASM or the JS API that would make it easy to have like a call that does some work the first time and then sort of patches in when it's done the work and then moves on as if it's direct call from then on, rather than having to do the call and direct and have the overhead, because that overhead we basically don't need anymore, or we know.
Right, some sort of mechanism for turning this call indirect and like patching it to be a direct call at some point. That would be interesting. We'd want to measure the overhead from all these call indirects. I expect it won't be large in some cases, but I'm sure we could construct examples where it would be a large overhead.
This is where the module linking would help, actually.
Okay. I should go read that proposal again.
Because it turns what is purely declarative into there's executable code in effect that does the linking.
Interesting. Yeah, I'll have to go see if that's compatible with the time separation between the initial instantiation of the module and then later you're going to patch in a bunch of extra stuff, right? So that's kind of, yeah, I'll have to read the proposal to see if that'll work.
It's 1 o'clock now. Are there any more pressing questions people have, and any more sort of items that you want to throw out, Thomas, before we wrap up?
That's it, really. Get in contact. Ross has my email if you're interested in this, if you want to do any work on it or anything like that. As I said, we haven't really started this yet, so if anyone wants to sort of do anything with it, you're totally welcome to.
or give you use cases even.
Yeah, just tell me, support this. Yeah, that's great.
Well, thanks very much, Thomas, for sort of being my guinea pig and trying the first one. I think you did a great job, and I really appreciate the awesome talk. So, and thanks for the great discussion also afterwards, so everyone in the audience.
Thank you. It was very, very
Yeah.
interesting.
I'm glad.
So, as I said, the next one is on Friday, October 24th at 4 p.m. Eastern time.